Welcome to Deep Sleep Manufacturing. I am your guide through one of the most fascinating and hypnotic environments on Earth, a modern automated food manufacturing facility. Tonight, we invite you on an extended, detailed journey through the intricate world of industrial food production. This is not merely a documentary about manufacturing. This is an immersive experience designed to transport you to a place where precision, rhythm, and mechanical harmony combine to create the perfect conditions for rest and relaxation. Imagine stepping through the main gates of a sprawling food factory at precisely 5:47 in the morning. The sky is still dark, but the facility is already coming alive. Outside, the cool morning air carries the faint scent of raw ingredients. Inside, the facility hums with quiet anticipation. Thousands of sensors are already recording data. Hundreds of motors are warming up. Temperature control systems are achieving perfect stability. The facility is not yet at full production, but it is preparing itself for a day of relentless, mechanical precision. As you walk deeper into the facility, you notice something remarkable about the environment. There are no workers rushing about. There are no raised voices or sudden loud noises. Instead, there is a calm, methodical silence broken only by the gentle hum of machinery, the soft beeping of sensors, and the rhythmic movement of conveyor systems. The facility operates with the quiet efficiency of a Swiss watch, every component functioning in perfect harmony with every other component. This is the world of automated food manufacturing. A world where individual human workers are almost absent, replaced by machines designed with such precision that they can reproduce the exact same action millions of times without error. A world where temperatures are controlled to within 1/10 of a degree. A world where weights are measured to the nearest gram. A world where the passage of time is divided into microseconds, each one accounted for, each one purposeful. The facility we are visiting today produces 2.4 million individual food products every single day. Each product is identical. Each product is perfect. Each product has passed through 47 separate quality checkpoints. The facility operates continuously, 24 hours per day, 365 days per year. The machinery has been running continuously for so long that the workers have memorized every sound, every rhythm, every pattern. They can diagnose problems by listening to subtle changes in the acoustic environment. In this extended journey, we will explore every stage of the manufacturing process in meticulous detail. We will examine the raw materials as they arrive. We will follow their transformation through multiple stages of processing. We will witness the application of coatings, the addition of flavorings, and the precision quality control systems that ensure perfection. And finally, we will see the finished products being packaged, labeled, and prepared for distribution to millions of consumers around the world. Close your eyes if you wish. Allow your breathing to synchronize with the rhythm of the machinery. Let your mind drift with the gentle flow of products through the facility. And prepare yourself for a journey that will take you deeper into the world of industrial precision than you have ever gone before. The food manufacturing facility we are visiting spans an area equivalent to 15 professional football fields. It contains 47 separate processing areas, 320 individual machines, and over 12 kilometers of conveyor belts. The facility employs 847 workers, though you might see only a handful of them during our entire journey. The workers are spread across 3 shifts, monitoring systems, performing maintenance, and making adjustments when the machines need human intervention. Let us begin our journey at the receiving department, where everything starts. The receiving dock is a massive open area, approximately 120 meters long and 45 meters wide. Its concrete floor is marked with precision lines indicating the exact positions where trucks should park. These parking positions are not random. They are positioned so that the loading machinery can reach exactly where it needs to reach, with no wasted movement, no inefficiency. As we watch, a massive refrigerated truck pulls into dock position number 7 at exactly 6:15 in the morning. The truck is 22 meters long and 2.6 meters high. Its cargo holds 24,000 kilograms of liquid milk, maintained at precisely 4 degrees Celsius throughout its journey from the dairy cooperative 127 kilometers away. The driver climbs down from the cab and performs a visual inspection, checking that the seal on the cargo compartment has not been broken, verifying the temperature reading on the external monitor. Once the truck is secured in position, using massive hydraulic clamps that hold it in place, a worker approaches with a clipboard. The checklist is simple but thorough. He notes the time of arrival, 6:15. He notes the truck identification number. He notes the external temperature reading. He notes the seal condition. All of this information is entered into a computer terminal, and within seconds, this data has been transmitted to the central quality control facility. A valve connection is established between the truck's cargo compartment and a rigid stainless steel pipe that leads into the facility. This connection process takes exactly 4 minutes and 23 seconds. It is always the same. The pipes are connected in a specific sequence. First the large diameter intake pipe, then the return pipe, then the drain valve. Only after all 3 connections have been established and verified does the transfer begin. Inside the facility, in a hidden room that few workers ever see, a series of massive stainless steel tanks wait to receive the milk. The tanks are arranged in 4 rows of 3, making 12 tanks total. Each tank is cylindrical, standing 3.2 meters tall and 2.1 meters in diameter. Their capacity is 3,500 liters each, for a total capacity of 42,000 liters across the entire receiving bay. 8 of these tanks are currently in use. The other 4 are being cleaned by an automated CIP, a clean-in-place system, that circulates heated water and cleaning solution through the tank's internal passages at high speed, removing any residual product from the previous day's operations. As we watch, a pump begins to operate. It is a positive displacement rotary pump, 45 centimeters in diameter. The pump begins to draw milk from the truck at a rate of 380 liters per minute. As the milk flows through a transparent section of the pipeline, it appears as a smooth, ivory-colored stream. Flow sensors continuously monitor the rate, ensuring it stays within the acceptable range of 375 to 385 liters per minute. If the flow rate begins to deviate, the system will automatically adjust the pump speed to correct it. The milk travels through multiple quality control stations before entering the storage tanks. First, it passes through a simple mesh strainer that removes any large particles that might have contaminated the milk during transport. This strainer is so fine that it can detect particles larger than 0.5 millimeters. Approximately 20 to 40 of these particles are removed from each tanker truck of milk. Nothing is wasted. These particles are flushed into a drain and eventually reach a water treatment facility. Next, the milk passes through an advanced particle counter. This device uses laser technology to count the exact number of particles in the milk, categorizing them by size. The sensor counts particles in 3 ranges: 2 to 5 micrometers, 5 to 10 micrometers, and larger than 10 micrometers. All of this data is recorded in real time and displayed on a monitor. If the particle count exceeds the acceptable threshold, an alarm will sound and the milk will be diverted to a separate tank for additional processing or rejection. Finally, the milk passes through a temperature sensor. The sensor displays the current temperature, 3.8 degrees Celsius. This is acceptable. The target temperature is 4 degrees Celsius, with an acceptable range of 3 to 5 degrees Celsius. As the milk has flowed through the system for the past 45 seconds, it has warmed slightly from the ambient temperature of the facility. But this is expected and acceptable. The milk now flows into tank number 3. We can see the level indicator on the side of the tank rising slowly. The current level is at 1,200 liters, marked by a thick red line painted on the stainless steel exterior. As the milk flows in, the level rises at approximately 380 liters per minute, meaning the level will rise by 6.3 centimeters every 60 seconds. The tank's total capacity is 3,500 liters, so it will take approximately 6 minutes and 4 seconds to completely fill the tank. Meanwhile, on the other side of the facility, a different truck has arrived with a different ingredient. This truck carries 18,000 kilograms of wheat flour. The flour is in sealed containers, 12 large metal barrels, each containing approximately 1,500 kilograms. The barrels are unloaded by a powered lift truck, carried to a specific location, and positioned under a pneumatic tube connection point. The flour transfer process is different from the milk transfer because flour is a dry ingredient. Instead of pumping liquid, the facility uses a pneumatic conveyor system. A large hose is connected to the first barrel, using a quick disconnect coupling that creates a hermetic seal. An air compressor, powered by a 15 kilowatt electric motor, begins to draw air from the barrel at a rate of 850 cubic centimeters per second. As the air is drawn, the flour is lifted from the barrel and flows through the hose at a rate of approximately 340 kilograms per minute. The flour is not transported directly into storage. Instead, it passes through multiple processing stages. First, it moves through a magnetic separator. This device contains a series of powerful magnets arranged in a cylindrical pattern. As the flour passes through, any metal particles, fragments of machinery, bolts, or other contaminants that might have accidentally entered the flour during harvesting or milling, are attracted to the magnets and removed from the main flow. The removed materials are collected in a small container and will be disposed of properly. After the magnetic separator, the flour moves through an optical sorter. This device is similar to the advanced equipment we will see later when processing individual products. A camera mounted inside the device scans each particle of flour. Actually, the camera does not scan individual particles, but rather examines the overall composition of the flour stream, detecting any discoloration or inconsistency that might indicate a problem. The optical sorter can detect problems at the rate of 40 samples per second, making it capable of analyzing approximately 13.6 million samples of flour per day. As the wheat flour flows through these processing stages, it is being continuously evaluated. The facility is not willing to accept flour that might be slightly off specification or contaminated in any way. The standards are uncompromising. The flour either meets the standards perfectly, or it does not enter the production process. Meanwhile, in another receiving dock, a truck has arrived carrying cocoa beans. These beans come from Ecuador, where they grow in tropical plantations. The cocoa beans have been shipped in heavy-duty cardboard boxes, 35 boxes per pallet, 4 pallets per truck. The beans are dark brown and emit a distinctive cocoa aroma that fills the receiving area. Workers carefully unload the pallets and move them to the cocoa receiving station. At the cocoa receiving station, samples of beans from each pallet are taken and sent to the laboratory for analysis. The analysis is comprehensive and includes the following tests: moisture content, fermentation level, bean size distribution, bean density, presence of mold or mildew, and chemical composition. The analysis takes approximately 45 minutes to complete. During this time, the pallets are held in a quarantine area and are not released to the production process until the analysis is completed and the results are approved. One pallet at a time, the cocoa beans are emptied into a large hopper. The hopper has a conical shape, designed so that the beans naturally flow downward toward an outlet. The outlet leads to a conveyor belt. The conveyor belt is moving at a speed of exactly 1.2 meters per second. This speed is not arbitrary. It has been calculated to allow the beans to flow smoothly without jamming, while also ensuring that the throughput rate matches the capacity of the downstream equipment. The conveyor belt can accommodate up to 850 kilograms of cocoa beans per minute. As the cocoa beans move along the conveyor belt, they are continuously observed by workers positioned at strategic points. The workers are looking for any visual anomalies, rocks, sticks, or other foreign objects that might have accidentally been included in the shipment. These workers are highly trained and experienced. They can identify problems in milliseconds. If a foreign object is detected, the worker pulls a cord. The cord is connected to an electromagnetic ejector. The ejector activates, and a pneumatic arm extends into the bean stream, deflecting the foreign object onto a separate conveyor belt where it will be removed. This process continues for hours. Truck after truck arrives. Ingredient after ingredient is received, inspected, and processed. Each ingredient follows its own unique pathway through the receiving department. Each ingredient is subject to its own specific quality control procedures. And all of this happens with a calm, methodical precision. There is no rushing. There is no impatience. The system operates according to a schedule that was established decades ago and has been refined continuously. Once the ingredients have passed the initial receiving inspections, they must be stored in conditions that preserve their quality and prevent degradation. This is where the facility's environmental control systems become critical. The storage areas are not simple warehouses. They are highly controlled environments where temperature, humidity, and air quality are monitored and adjusted continuously. Let us examine the milk storage area first. The 12 tanks we saw earlier are located in a dedicated refrigeration chamber. The chamber is insulated with 30 centimeters of spray foam insulation on all walls, the floor, and the ceiling. The insulation is designed to minimize heat transfer from the outside environment. Inside the chamber, the temperature is maintained at exactly 3.8 degrees Celsius by a sophisticated refrigeration system. The refrigeration system is remarkably complex. It consists of two completely independent refrigeration units, each capable of independently maintaining the required temperature. This redundancy is intentional. If one unit fails, the other unit automatically takes over. The system includes no single point of failure. There is no scenario in which the milk temperature could rise above 5 degrees Celsius due to equipment failure. Each refrigeration unit contains a compressor, a condenser, an expansion valve, and an evaporator. The compressor is a rotary screw compressor, 35 centimeters in diameter, powered by a 22 kilowatt electric motor. The compressor operates continuously when the temperature is above the set point, and cycles on and off when the temperature is at or below the set point. Inside the storage chamber, the actual cooling is accomplished by the evaporator, a series of aluminum tubing with metal fins attached. Cold refrigerant flows through the tubing at high speed. The metal fins are in direct contact with the air inside the chamber. As the warm air inside the chamber comes into contact with the cold fins, the air is cooled. A large fan, 1.2 meters in diameter, continuously circulates the air inside the chamber, ensuring that the temperature is uniform throughout the space. Temperature sensors positioned at various locations inside the chamber constantly monitor the temperature. If any sensor detects a temperature deviation of more than 0.2 degrees Celsius from the target, the system automatically adjusts the refrigerant flow to correct the situation. In addition to temperature control, the storage chamber includes a sophisticated humidity control system. Humidity sensors measure the relative humidity inside the chamber continuously. The target humidity is 65%, with an acceptable range of 60 to 70%. Humidity that is too high can lead to the growth of mold and mildew. Humidity that is too low can lead to evaporative loss of moisture from the milk, altering its composition. A dehumidifier and humidifier work together to maintain the humidity within the target range. The milk storage area also includes a backup power system. The entire facility is connected to the primary power grid, but the storage areas are additionally connected to a 400 kilowatt diesel generator. If the primary power fails, the generator automatically starts within 2 seconds. The generator is capable of powering all critical systems, including the refrigeration units, for as long as the diesel fuel supply lasts. The facility maintains a 30-day supply of diesel fuel in underground storage tanks. Now let us move to the dry ingredient storage area. This area is much larger than the milk storage area, covering approximately 2,400 square meters. It contains large silo systems for flour, sugar, cocoa powder, and various other dry ingredients. Each silo is cylindrical, made of stainless steel or carbon steel, and can hold from 5,000 to 50,000 kilograms of material, depending on the ingredient. The silo for wheat flour is the largest in the storage area. It stands 8.5 meters tall and is 3.2 meters in diameter. Its capacity is 42,000 kilograms, approximately 13 truckloads of flour. The interior of the silo has been specially designed to prevent the flour from compacting or bridging. A compaction bridging condition occurs when flour at the top of the silo is so tightly packed that it prevents the flour below from flowing freely. To prevent this, the interior walls of the silo are specially textured, and the outlet area is designed with a conical shape and a vibration system that keeps the flour moving smoothly toward the outlet. Attached to the bottom of the flour silo is a discharge valve. This valve is not a simple gate valve. It is an advanced rotary valve, specifically designed for handling fine powders like flour. The rotary valve contains a rotor with 4 pockets. As the rotor turns, each pocket moves in sequence into position at the outlet, allowing a measured amount of flour to fall into a conveyor system below. The rotation speed is variable and can be adjusted from 5 rotations per minute to 45 rotations per minute, allowing the facility to adjust the flour discharge rate from approximately 60 kilograms per hour to 540 kilograms per hour. The environment inside and around the silos is continuously monitored. Pressure sensors on the silo walls measure the pressure being exerted by the flour, allowing the control system to estimate the total flour level inside the silo without needing to physically look inside. When the flour level drops to 20% of capacity, 8,400 kilograms, an alarm sounds and a purchase order is automatically generated for additional flour to be shipped from the supplier. Moisture content sensors positioned inside the silos measure the moisture level of the flour continuously. Flour can absorb moisture from the air. If the moisture level rises above 12%, the quality of the flour can be affected, and it may not perform as expected in the manufacturing process. If a moisture sensor detects a moisture level above 12%, the system activates a desiccant system. Hot, dry air is circulated through the silo, reducing the moisture level back to the acceptable range. The sugar storage system is similar, but the sugar is stored in a different type of container. Sugar is hygroscopic, meaning it absorbs moisture from the air very readily. Sugar is stored in a sealed storage vessel, and the air inside the vessel is continuously dried using a sophisticated desiccant system. The desiccant material is silica gel. As the silica gel absorbs moisture, it becomes saturated. Before it becomes completely saturated, the system heats the silica gel, driving off the absorbed moisture and regenerating the desiccant. This process is continuous, keeping the sugar completely dry. The cocoa powder storage is special because cocoa powder is valuable and has a distinctive flavor that can be absorbed by other ingredients if not properly isolated. The cocoa powder is stored in sealed stainless steel containers, each holding 200 kilograms. These containers are stacked in the storage area, and they are not opened until the cocoa powder is needed in the production process. All storage areas are climate controlled. The temperature is maintained at 18 degrees Celsius, with a humidity of 55%. These conditions have been carefully selected to preserve the quality of all the ingredients without requiring extreme environmental controls that would be energy intensive. The facility is designed to be energy efficient while maintaining absolute quality control. Backup power systems, redundant sensors, and continuous monitoring create an environment where ingredient degradation is essentially impossible. The ingredients will sit in storage for days, weeks, or even months, and they will emerge in exactly the same condition as when they entered. When production begins on a given day, ingredients must be prepared and processed before they can be used in the actual product manufacturing. This preparation stage is critical and requires its own sophisticated equipment and procedures. Let us begin with the milk. The milk has been stored at 3.8 degrees Celsius for an average of 48 hours since it arrived. Before it can be used in the production process, it must be pasteurized. Pasteurization is a heat treatment process that eliminates harmful bacteria while minimizing the loss of nutrients and flavor compounds. The milk is pumped from the storage tank at a rate of 500 liters per minute. It flows through a complex piece of equipment called a pasteurization unit. This unit operates using a technique called high-temperature short-time pasteurization, or HTST. The milk is rapidly heated to 72 degrees Celsius, held at that temperature for exactly 15 seconds, and then rapidly cooled back to 4 degrees Celsius. The heating section of the pasteurization unit contains a large stainless steel vessel that is surrounded by circulating hot water. The hot water is maintained at 85 degrees Celsius. As the milk flows through tubes submerged in the hot water, it is heated gradually. Temperature sensors measure the milk temperature continuously. When the temperature reaches 72 degrees Celsius, the milk flows into the holding tube. The holding tube is 3.5 meters long. At the flow rate of 500 liters per minute, the milk takes exactly 15 seconds to traverse the holding tube. This 15-second holding time is critical. It is long enough to eliminate harmful bacteria, but short enough that the milk's flavor and nutritional content are minimally affected. After the holding tube, the milk flows into the cooling section. The cooling section is similar to the heating section, but in reverse. Cold water maintained at 2 degrees Celsius circulates around the cooling tubes. As the milk flows through the cooling tubes, it is cooled rapidly. By the time it exits the cooling section, the milk temperature is 4 degrees Celsius. The pasteurization process occurs continuously, 24 hours per day. Every moment, milk is being heated, held, and cooled. The system operates with such precision that the milk temperature never exceeds 72.3 degrees Celsius or drops below 71.7 degrees Celsius during the holding time. Similarly, the cooling is so efficient that the milk temperature never exceeds 4.5 degrees Celsius as it exits the cooling section. Now let us examine the flour preparation. The flour exits the silo at a rate of 240 kilograms per minute and lands on a conveyor belt. The conveyor belt is moving at 1.5 meters per second. The flour forms a layer approximately 10 centimeters thick on the conveyor belt, moving steadily forward. As the flour moves along the conveyor belt, it passes underneath a series of optical sensors. These sensors scan the flour continuously, looking for any signs of contamination, insects, insect fragments, or other foreign material that might have been missed by the previous inspection stages. If the sensors detect anything unusual, they trigger an ejector that removes the contaminated section of flour from the conveyor belt. The flour then enters a flour conditioning system. This system adds a small amount of water to the flour, approximately 0.5% by weight. This water addition is carefully controlled. A water injection system sprays fine mist water onto the flour as it moves along a conveyor belt. The water spray is followed by a mixing section, where rotating paddles gently mix the moisturized flour, ensuring even distribution of the water throughout the flour. Why add water to the flour? The answer lies in the chemistry of dough formation. Flour that is too dry does not hydrate properly when water is added later in the mixing process. By pre-moisturizing the flour, the facility ensures that the flour will hydrate evenly when larger amounts of water are added in the main mixing tanks. This results in more uniform dough characteristics and more consistent final products. After conditioning, the flour passes through a temperature adjustment system. The flour is now at room temperature, approximately 22 degrees Celsius. However, the production process operates most efficiently if the flour is at a temperature of 18 degrees Celsius. A cooling section removes approximately 4 degrees of heat from the flour. The cooling section is a sealed chamber through which cool air at 15 degrees Celsius is circulated. The flour moves through this chamber on a conveyor belt for 8 minutes. By the time it exits, the flour temperature has dropped to exactly 18 degrees Celsius. The cocoa beans require more extensive preparation. First, the beans must be roasted. Roasting develops the cocoa flavor and makes the beans easier to process. The roasting process begins when beans are fed into a large rotating drum, 2 meters in diameter and 3 meters long. The drum is heated to 140 degrees Celsius using steam that circulates through the drum's jacket. The beans tumble and roll inside the drum as it rotates slowly at 4 rotations per minute. The roasting process must be carefully controlled. If the beans are roasted too little, the flavor will not develop properly. If the beans are roasted too much, the flavor will become bitter and unpleasant. The facility monitors the roasting process by periodically removing small samples of beans and analyzing them. The analysis measures the color of the beans, the moisture level, and the volatility of flavor compounds. The roasting time is exactly 24 minutes. This duration has been determined through extensive experimentation to be optimal for the specific product being manufactured. When 24 minutes have elapsed, the roaster drum stops rotating. A large door opens and the hot beans cascade into a cooling chamber. The cooling chamber is a large steel vessel filled with cool air at 10 degrees Celsius. A conveyor belt carries the beans through the chamber slowly. The beans move through the chamber for 18 minutes, during which time they are cooled from 140 degrees Celsius to 25 degrees Celsius. After cooling, the cocoa beans are moved to a winnowing station. Winnowing is the process of removing the cocoa shell from the cocoa nib, the actual edible part of the bean. The winnower contains a series of screens and air currents. The beans are cracked into small pieces, and then air currents separate the lighter shells from the heavier nibs. The cocoa shells are sent to a separate facility for other uses, while the cocoa nibs are collected and transported to the next processing stage. The cocoa nibs are now roasted again for a shorter duration, 8 minutes, to further develop the flavor. After this secondary roasting, they are cooled again, and then they are ground into cocoa powder. The grinding process uses a large cylindrical mill, 1.5 meters in diameter. The cocoa nibs feed into the top of the mill. Inside the mill, large grinding stones rotate at 120 rotations per minute. The cocoa nibs are crushed between the grinding stones, and the resulting cocoa powder exits from the bottom of the mill. The cocoa powder is exceptionally fine. It is sifted through a mesh screen with an opening size of 0.1 millimeters. Some powder is too coarse and does not pass through the screen. This coarse powder is recycled back to the grinder. Only the finest powder continues forward to the production process. Throughout all these preparation stages, the ingredients are being continuously monitored and adjusted. Sensors measure temperature, moisture, particle size, and many other parameters. The control systems make continuous adjustments, ensuring that every ingredient emerges from the preparation stage in exactly the condition needed for the next stage of manufacturing. The prepared ingredients now converge at the heart of the manufacturing facility, the mixing hall. This is a vast open space, 60 meters long, 40 meters wide, and 12 meters high. The ceiling is supported by massive steel beams spaced 10 meters apart. The floor is stainless steel, sloping gently toward drainage points so that any spilled ingredients can be quickly cleaned up and safely disposed of. In this mixing hall, there are 12 enormous mixing tanks arranged in a precise grid pattern. Each tank is cylindrical, standing 4.2 meters tall and 2.8 meters in diameter. The total volume of each tank is 25,000 liters. The tanks are made of stainless steel, 6 millimeters thick, capable of withstanding enormous internal pressures. At any given moment, multiple mixing batches are underway. We are watching tank number 7. The tank is currently empty, and it has just completed a cleaning cycle. A cleaning validation sensor has confirmed that the tank is clean and free of any residual material from the previous batch. The mixing process begins with the addition of the liquid base. A flexible hose, 5 centimeters in diameter, extends from the pasteurized milk tank to the top of mixing tank number 7. A pump begins to operate and milk flows into the tank. The milk falls vertically downward into the tank, creating a gentle waterfall effect that we can hear from outside the tank. The flow rate is 3,000 liters per minute. At this rate, the tank will be filled with 15,000 liters of milk in exactly 5 minutes. As the milk accumulates in the tank, its level rises. A level sensor monitors the height of the milk continuously. When the level reaches 1.5 meters, the point at which 15,000 liters have been added, the milk flow automatically stops. There is no overfill. The system is so precisely calibrated that the milk stops flowing exactly when the target volume is reached. Now begins the next phase. Sugar syrup must be added. The sugar syrup has been prepared in a separate location. Sugar has been dissolved in hot water at a ratio of 60% sugar to 40% water. The syrup is warm, 48 degrees Celsius, and has a density higher than water. A flow meter measures the sugar syrup as it is pumped into the milk. The flow rate is 850 liters per minute. Exactly 2,800 liters of sugar syrup are added. The addition takes 3 minutes and 18 seconds. As the sugar syrup flows into the milk, a marbling effect is visible. The golden brown syrup swirls through the white milk, creating beautiful spiral patterns. But these patterns will not persist. A mixing paddle is about to begin its work. The mixing paddle is the largest single component inside the tank. It is shaped like a giant anchor, extending from the top of the tank to near the bottom. The paddle is 3.5 meters tall and is constructed of stainless steel tubing, with blades of thin stainless steel sheet welded to the frame. The paddle is positioned so that it hangs vertically inside the tank, with approximately 20 centimeters of clearance between the paddle and the tank walls. The mixing paddle is connected to a variable speed drive motor mounted above the tank. The motor is powered by a 22 kilowatt electric supply. The motor can rotate the paddle at speeds ranging from 5 rotations per minute to 80 rotations per minute. For this particular mixing operation, the paddle is set to rotate at 12 rotations per minute. The paddle begins to rotate. As it rotates, the paddle moves downward and upward through the mixture. One complete rotation takes 5 seconds, moving down for 2.5 seconds and up for 2.5 seconds. As the paddle moves through the mixture, the blades cut through the liquid, breaking up any swirls or layered regions, and blending the ingredients into a uniform mixture. The mixing process takes exactly 24 minutes. During this time, the paddle continues to rotate at 12 rotations per minute. The paddle will complete 288 complete rotations. After the final rotation, the motor stops. The paddle hangs motionless inside the tank. But the mixing is not yet complete. Additional ingredients must be added, and each addition must be carefully integrated into the mixture. A precision metering system adds 560 kilograms of conditioned flour. The flour is added very slowly, 1.2 kilograms per minute. This slow addition is critical. If flour were added too quickly, it would form lumps that would be nearly impossible to break up and dissolve. The flour is added through a special port in the top of the tank. As the flour falls into the tank, it initially floats on the surface of the liquid due to the air pockets between the flour particles. But the paddle is still rotating, albeit more slowly now, at only 4 rotations per minute. The slow paddle rotation gradually pulls the floating flour down into the liquid, and the flour becomes thoroughly hydrated and integrated into the mixture. After the flour addition is complete, 280 kilograms of cocoa powder is added. Again, the addition is slow, 2.1 kilograms per minute. The cocoa powder is dark and dense. As it falls into the tank, it immediately sinks to the bottom, creating a dark layer at the base of the tank. The rotating paddle at 4 rotations per minute gradually mixes this cocoa powder upward and distributes it evenly throughout the entire mixture. Next, various additives are added in precise quantities: 8.4 kilograms of vanilla flavoring, 12.2 kilograms of lecithin emulsifier, 4.7 kilograms of xanthan gum thickening agent, 0.8 kilograms of salt, and 3.2 kilograms of preservative. Each additive is delivered through a separate port and is measured precisely using electronic scales. As each additive is added, the paddle speed is adjusted to ensure optimal mixing. The total mixing time from start to finish is 31 minutes. During this time, multiple sensors are continuously monitoring the mixture. A viscosity probe measures the thickness of the mixture. A temperature sensor monitors the temperature. A pH sensor monitors acidity. As each ingredient is added, the sensors record the response. The data is displayed on a large screen in the control room, where an operator can observe the progress of the mixing. After 31 minutes, the mixing cycle is complete. The mixture is now a perfectly uniform chocolate-colored liquid with the consistency of thick cream. Every milliliter of the mixture has the same composition as every other milliliter. The mixture is ready for the next stage of processing. The mixed product must now be formed into individual pieces. The forming process is accomplished by a highly sophisticated machine called a depositor. The depositor is designed to portion the mixture and shape it into the final product form. The product flows from the mixing tank through a 3 cm diameter hose into the depositor's receiving hopper. The hopper is a funnel-shaped steel vessel 45 centimeters tall that holds approximately 200 liters of the mixture. As the mixture flows into the hopper, it settles downward, and the air that was mixed in during the preparation phase gradually rises to the surface and escapes. Below the hopper is a large pump called a gear pump. The gear pump is a positive displacement pump, meaning it delivers exactly the same amount of fluid with every rotation, regardless of the pressure it must work against. The pump's displacement is 28 milliliters per rotation. The pump is driven by an electric motor that rotates at 1,560 rotations per minute. This means that the pump delivers exactly 28 times 1,560 is equal to 43,680 milliliters per minute, or approximately 44 liters per minute. But wait, the pump delivers much more than the amount of product that is supposed to be dispensed for each product portion. The answer lies in a sophisticated metering system. Between the pump and the forming chamber, there is a proportional control valve. This valve can be adjusted from 0 to 100% open. When the valve is fully open, the maximum amount of product flows to the forming chamber. When the valve is partially open, less product flows to the forming chamber. The remainder of the product is diverted through a recirculation line back into the receiving hopper, where it will be pumped again and again until it is finally sent to the forming chamber. For each portion, the proportional control valve is open for exactly 1.34 seconds. During this time, the product flows into the forming chamber at a rate of 44 liters per minute. In 1.34 seconds, 4460 times 1.34 is equal to 0.986 liters, or approximately 1 liter, flows into the forming chamber. Since the density of the product is approximately 1.08 kilograms per liter, this means 1.08 kilograms of product is dispensed into each forming chamber. Wait, we said earlier that each product weighs 43.7 grams. not 1.08 kilograms. The discrepancy is because multiple products are being formed simultaneously. The forming chamber is not a single mold, but rather a carousel containing 52 individual molds. Each mold is cube-shaped, measuring 4 centimeters on each side. The carousel rotates, bringing a new mold into position at the dispensing point every 1.34 seconds. As the carousel rotates, the product is dispensed into the mold. But the product does not simply fill the mold. It is extruded through a special nozzle that shapes the product as it falls into the mold. The nozzle is designed to create a specific shape. As the product flows through the nozzle directs it so that it lands in the mold in a precise configuration. Some portions of the product are directed to the center of the mold, while other portions are directed to the sides. The result is that each mold is filled with a shaped product that already approximates the final form of the product, even before the forming press applies its pressure. Once a mold has been filled, the carousel rotates, bringing the next empty mold into the dispensing position. The filled mold moves to the next station, the forming press. The forming press consists of 2 powerful hydraulic presses, one on the top and one on the bottom of the carousel. The top press descends rapidly and the bottom press rises. They meet at the mold, exerting enormous pressure on the product inside. The pressure applied is 1,500 kilograms per square centimeter. At this pressure, the product is compressed, any air bubbles are removed, and the product is shaped into its final form. The pressure is applied for exactly 6 seconds. Then the presses retract and the carousel rotates again, bringing the formed product to the next station. The next station is a cooling station. The carousel rotates continuously, passing each mold through a series of cooling chambers. The cooling chambers are sealed boxes, within which cold air at 5 degrees Celsius is circulated continuously. The molds pass slowly through the chambers. Each mold spends 45 seconds in a cooling chamber. After this time, the product inside the mold has cooled sufficiently that it can be safely removed from the mold without deforming. The cooling is carefully controlled because the rate of cooling affects the final texture of the product. If the product is cooled too quickly, it can become brittle. If it is cooled too slowly, it may remain slightly soft and malleable. The cooling rate of 5 degrees Celsius per minute has been determined to be optimal for the product characteristics desired. After cooling, the carousel moves to the ejection station. At this station, a system of pneumatic fingers, small air-powered robotic arms, reaches into each mold and grasps the formed product. The fingers withdraw from the mold, pulling the product out. The product emerges intact, fully formed, and ready for the next processing stage. The formed product lands on another conveyor belt. This belt is moving at 1.2 meters per second. The products are arranged on the belt in a single file line, spaced approximately 15 centimeters apart. The belt moves the products toward the next processing stage, surface treatment and coating. Throughout the entire forming process, the timing is absolutely critical. The carousel must rotate precisely every 1.34 seconds. The forming presses must exert pressure for exactly 6 seconds. The cooling must progress at exactly 5 degrees Celsius per minute. The ejection must occur at precisely the right moment. If any of these timings were even slightly off, the product quality would be compromised. But the equipment is so precise that the timing never varies. It is always the same every time, every day, year after year. The formed products are now ready for surface treatment. Some products will receive a chocolate coating. Others will receive a sugar coating. Still others will receive a combination of coatings and flavoring agents. The coating stage is one of the most visually satisfying stages of the entire manufacturing process. Let us follow the products that are destined to receive a chocolate coating. The products move along a conveyor belt toward a chocolate melting station. The chocolate melting station is a large stainless steel vessel, 1.2 meters in diameter, heated by circulating hot water. Solid chocolate has been loaded into the vessel, approximately 200 kilograms. The chocolate is brown and has an aroma that fills the surrounding area. As the water circulates through the vessel's jacket at a temperature of 50 degrees Celsius, the chocolate gradually melts. The melting process takes approximately 45 minutes. As the chocolate melts, the consistency becomes increasingly smooth and fluid. A large paddle, rotating at 3 rotations per minute, gently stirs the chocolate, ensuring that the melting is uniform throughout the vessel. When the chocolate is fully melted, its temperature is exactly 46 degrees Celsius. This temperature is critical. If the chocolate is hotter, it will be too thin and will not coat the products adequately. If it is cooler, it will be too thick and will not flow smoothly. The temperature is monitored continuously by sensors, and if it begins to deviate from 46 degrees Celsius, the water circulation system automatically adjusts to correct the temperature. The chocolate now flows through a tube toward the enrobing machine. The enrobing machine is perhaps the most spectacular piece of equipment in the entire facility. It consists of a long conveyor belt that moves through a chamber. At the entrance to the chamber, a massive waterfall of chocolate cascades downward. The products are placed on the conveyor belt before the waterfall. As the conveyor belt moves forward, each product passes directly beneath the chocolate waterfall. The waterfall is created by a shaped nozzle at the top of the machine. Chocolate flows through the nozzle at a rate of 850 liters per minute. The nozzle is shaped to create a smooth, continuous curtain of chocolate. The thickness of the chocolate curtain is 8 millimeters. The width of the curtain is 1.2 meters, wide enough to coat multiple products simultaneously. Each product spends exactly 2.4 seconds under the chocolate waterfall. During this time, the chocolate cascades over the product from above, coating the top and sides with a layer of glossy chocolate. As the product exits the waterfall, excess chocolate drips downward from the product. These chocolate drippings are collected in a channel at the bottom of the machine and are returned to the chocolate reservoir for recycling. No chocolate is wasted. After the waterfall, the products move onto a vibrating section of the conveyor belt. This section vibrates side to side at a frequency of 120 cycles per second. The vibration causes any excess chocolate clinging to the product to shake loose and drip off. The vibration continues for 8 seconds, the time it takes for the products to traverse this section of the conveyor. The rate of vibration is constant and precise, always 120 cycles per second, never varying. The products now move into a cooling tunnel. This tunnel is long, 24 meters, and is filled with air at 8 degrees Celsius. The products move through the tunnel at a speed of 0.8 meters per minute. At this speed, the transit time is 30 minutes. During this 30 minutes, the chocolate gradually cools and hardens. The cooling is not rapid. The product temperature drops at a rate of approximately 2.5 degrees Celsius per minute. This slow cooling is important because it allows the chocolate to crystallize in the proper crystal structure, resulting in a smooth, glossy finish and a pleasant snap when the product is bitten. After the cooling tunnel, the products emerge with a perfect chocolate coating. The coating is smooth, uniformly thick, and has a beautiful glossy appearance. The products are now ready for the quality inspection and packaging stages. Meanwhile, other products have been following a different path. These products are receiving a different type of coating, a finely granulated sugar shell. The sugar coating machine works differently from the chocolate coating machine. Instead of a waterfall, it uses a drum coating approach. In the drum coating system, the products are placed into a large rotating drum. The drum is 1.5 meters in diameter and 2 meters long. The interior of the drum contains a series of lifting blades. As the drum rotates at 6 rotations per minute, the lifting blades lift the products upward and then allow them to cascade downward. This tumbling motion is continuous. As the products tumble inside the drum, a fine mist of sugar syrup is sprayed into the drum. The sugar syrup is warm, 50 degrees Celsius, and has a viscosity similar to thick honey. The spray is applied at a rate of 12 liters per minute. The sugar syrup lands on the products and sticks to them. Simultaneously, dry sugar crystals are also sprayed into the drum at a rate of 8 kilograms per minute. The sugar crystals stick to the sugar syrup coating, building up a granulated sugar shell. The process continues for 8 minutes. During this time, the products are continuously tumbled, and they accumulate multiple layers of sugar coating and sugar crystals. After 8 minutes, the products have accumulated a sugar shell approximately 2 millimeters thick. The drum stops rotating and a chute opens at the bottom of the drum. The sugar-coated products slide down the chute onto another conveyor belt, which carries them toward the cooling and drying stage. The sugar-coated products move through a drying tunnel where warm air at 35 degrees Celsius is circulated. The warm air removes any residual moisture from the sugar coating, ensuring that the coating is completely hard and crispy. The drying takes 12 minutes. After this time, the products emerge with a firm, crunchy sugar shell. All products, regardless of their coating type, now converge at the quality control inspection line. This line is where the facility's final verification occurs before products are allowed to proceed to packaging. The inspection line is a marvel of artificial intelligence and sensor technology. The line moves at a rate of 1 product per 1.2 seconds. As each product arrives at the inspection station, it is photographed by 5 high-resolution cameras simultaneously. The cameras capture images from 5 different angles: top, bottom, and 3 sides. These 5 images are transmitted to an artificial intelligence system in real time. The AI system has been trained on thousands of images of perfect products. It compares the images of the product being inspected to the reference images of perfect products. The AI analyzes multiple parameters: color uniformity, surface texture, size and dimensions, coating thickness, and general shape. The analysis takes 0.3 seconds. Simultaneously, the product passes through a weight measurement station. The product is positioned on a precision electronic scale. The scale measures the product weight to the nearest 0.1 gram. The target weight is 43.7 grams. The acceptable range is 43.2 to 44.2 grams. The scale provides the weight measurement in 0.2 seconds. If the weight is within the acceptable range, the product passes this inspection. If the weight is outside the range, the product is flagged. The product now passes through a metal detector. The metal detector uses electromagnetic induction to detect the presence of any ferrous metals, non-ferrous metals, or stainless steel that might have accidentally contaminated the product during processing. The metal detector produces a signal that is analyzed by a computer. If the signal indicates the presence of metal, the product is flagged. Finally, the product passes through an X-ray imaging system. The X-ray system creates an image of the internal structure of the product, revealing the distribution of ingredients and identifying any voids or irregularities that might not be visible on the exterior. The X-ray analysis takes 0.4 seconds. All of this analysis, visual inspection by AI, weight measurement, metal detection, and X-ray analysis, takes less than 2 seconds total. As soon as the analysis is complete, a decision is made. Is the product acceptable or is it defective? If the product is acceptable, it is allowed to continue forward to the packaging line. If the product is defective, a pneumatic ejector is activated. The ejector provides a sharp air pulse that deflects the product from the main conveyor belt onto a secondary conveyor belt. This secondary belt carries the defective products to a rework area. The defective products will be melted down, mixed with fresh material, and reformed. They will pass through the entire manufacturing process again. The acceptance rate in this facility is very high, typically 98.7%. This means that for every 1,000 products manufactured, approximately 13 products are rejected and sent for rework. Most of these rejections are due to weight being outside the acceptable range. Very few rejections are due to contamination, defects, or other quality issues. The facility's quality control systems are so effective that serious problems are virtually eliminated. The acceptable products now proceed to the packaging department. This department is where individual products are placed into consumer-facing packages. The packaging machine is a high-speed automatic system capable of packaging 2,400 products per hour. This translates to one package being completed every 1.5 seconds. The machine operates continuously with no breaks, no pauses, no inefficiency. The products arrive on a conveyor belt at a rate of one product per 1.2 seconds. They are guided into the entrance of the packaging machine by a funnel-shaped chute. The chute focuses the products into a single file line, with products spaced exactly 15 centimeters apart. Each product enters a package placement chamber. Inside the chamber, a servo motor actuates a robotic arm. The robotic arm has a vacuum gripper mounted on its end. The gripper creates a vacuum seal on the top surface of the product. This vacuum holds the product securely in place. The robotic arm lifts the product from the conveyor belt and positions it inside an empty package. While the robotic arm is positioning the product, another servo motor has actuated a second robotic arm that has placed an empty package into the packaging chamber. The package is a cardboard box, pre-folded, with an open top. The dimensions are 12 centimeters length, 8 centimeters width, and 6 centimeters height. The box weighs 12 grams. The product is placed inside the box. The robotic arm releases the vacuum, and the product settles into the bottom of the box. Simultaneously, the flaps of the box are folded closed over the top of the product. A mechanical mechanism folds each flap in sequence, creating a closed package. Once the flaps are closed, the package is conveyed to the sealing station. At the sealing station, an adhesive applicator applies a bead of hot melt adhesive to the seams where the flaps meet the box. The adhesive is applied in a precise pattern, 5 millimeters wide, 8 centimeters long. The amount of adhesive applied is 2.3 milliliters per package. As the adhesive cools, it hardens, creating a bond that is permanent. The sealed package then moves to the labeling station. The labeling station includes a printer and an applicator. The printer prints product information directly onto a label. The information includes the product name, the weight, the ingredient list, the nutritional information, the manufacturing date, the expiration date, a barcode, and various regulatory markings and certifications. The label printing takes 0.8 seconds. The label is precisely positioned and applied to the package by a servo-controlled applicator. The label is centered on the package to within 0.5 millimeters. The label placement is so precise that if you were to examine 10,000 packages, you would not find a single label that was misaligned. A barcode scanner reads the barcode on each package to verify that the correct information has been printed. The scanner reads the barcode in 0.3 seconds. If the barcode is unreadable, the package is diverted for correction. The packaged products are now complete. They have been sealed and labeled. They are ready for case packing and distribution. Individual packages are now transported on another conveyor belt toward the case packing area. The case packing area is where individual packages are grouped together into larger cases for shipping. A robotic case packing system handles this stage. The system consists of a series of robotic arms arranged in a configuration that allows them to work together efficiently. One robot is responsible for opening cases. A second robot is responsible for picking up packages and arranging them into cases. A third robot is responsible for closing cases. The process begins when an empty cardboard case is placed into the case packing system. The case is a shipping case, much larger than the individual product packages. It measures 40 centimeters long, 30 centimeters wide, and 35 centimeters high. The case is designed to hold exactly 24 individual product packages, arranged in 4 rows of 6 packages each. The first robotic arm reaches toward the case and grasps the top flaps. It lifts the flaps open, preparing the case for filling. The second robotic arm reaches toward the conveyor belt of individual packages. Using a vacuum gripper, it grasps a package, lifts it from the conveyor, and positions it in the case. The package is placed in position with extremely high precision. The placement is accurate to within 2 millimeters. The robot then releases the vacuum and returns to grasp the next package. This process continues with the robot placing packages one by one into the case. The placement is in a specific pattern. The first package goes to the bottom left corner of the case. The second package is placed to the right of the first. The third package is placed to the right of the second. After 6 packages have been placed, the first row is complete. The robot returns to the first position and begins placing the second row, then the third, then the fourth. The placement of all 24 packages takes exactly 36 seconds. After the final package has been placed, the case is full. The third robotic arm now comes into action. This arm grasps the top flaps of the case and pulls them closed. The flaps fold over the packages and fold flat against each other. The robotic arm applies firm pressure to ensure that the flaps are completely flat. An adhesive applicator now applies a bead of strong adhesive along the seams of the case. The adhesive is different from the adhesive used for product packages. This adhesive is much stronger, capable of withstanding the vibrations and stresses of shipping. The adhesive is applied along the 2 seams where the flaps meet the sides of the case. The case now moves to a case labeling station. A label is applied to the case, showing the shipping address, the contents of the case, the manufacturing date, and a barcode. The barcode is scanned to verify the contents of the case. The sealed and labeled case is now placed onto a pallet. A pallet is a wooden platform measuring 120 centimeters by 100 centimeters. Cases are stacked onto the pallet in a precise pattern. The first layer contains 12 cases arranged in 2 rows of 6 cases each. A second layer of 12 cases is stacked on top of the first layer. A third layer is added for a total of 36 cases per pallet. The loaded pallet is shrink-wrapped by a shrink-wrap machine. The machine surrounds the pallet with a clear plastic film. Hot air then passes over the plastic, causing it to shrink tightly around the cases. The shrink wrapping holds all the cases firmly in place, preventing them from shifting during transport. The shrink-wrapped pallet is now moved into a warehouse storage area using a powered forklift truck. The warehouse is a massive building, 150 meters long, 100 meters wide, and 15 meters high. The warehouse contains thousands of pallets arranged in neat rows on high-capacity racking systems. The racking systems are designed so that pallets can be stored in multiple rows, one in front of another, with each row holding 12 pallets. The new pallet is positioned in an empty spot on the racking system. A computer system records the exact location of the pallet in the warehouse. This information is stored in a database. When an order comes in from a customer, the warehouse system can instantly locate the correct pallet, and forklift operators can retrieve the pallet and prepare it for shipment. The product has now completed its journey through the manufacturing facility. From raw ingredients to finished products in warehouse storage, the entire process has taken several hours. During that time, the product has been subject to dozens of processing steps, hundreds of quality control checks, and countless precise measurements and adjustments. We have now journeyed through the complete food manufacturing process, from the arrival of raw ingredients to the storage of finished products in the warehouse. Throughout this journey, we have witnessed the remarkable precision of modern manufacturing. The facility operates with a consistency and reliability that is almost impossible to comprehend. Every day, this facility produces exactly the same amount of product. Every product is identical. Every product has passed the same quality control procedures. Every product has been packaged in exactly the same way. The consistency is absolute. The precision is unwavering. As you rest and drift into sleep, remember that the processes you have witnessed continue endlessly. Even as you sleep, ingredients are arriving at receiving docks. Machines are mixing, forming, coating, and packaging. Quality control systems are inspecting products. Warehouse systems are organizing shipments. The facility never stops. The machinery never tires. The precision never wavers. The next time you consume a food product, a chocolate, a biscuit, a confection, take a moment to appreciate the remarkable complexity that went into creating that product. It was not created by a person working in a kitchen. It was created by sophisticated machines, operated by skilled technicians, monitored by artificial intelligence, and verified by dozens of quality control systems. And perhaps the next time you need to sleep, return to this facility. Let the rhythm of the machinery lull you to rest. Let the precision and order of the processes calm your mind. Let yourself drift into sleep knowing that somewhere in the world, this marvelous facility is continuing its eternal work. Sleep well. Dream peacefully. And when you wake, you will understand the remarkable precision of the world that surrounds us.